Ionized Yeast presents Lights Out, Everybody.
Good morning. Thanks to the electricity situation in our classroom, we were unable to meet today. As a result, I'm going to talk about the lecture material that I was going to look at today in this video. Also, it's been requested that I elaborate a little bit on this whole bisection Newton false position thing. So we'll do that in the next video. Numerical analysis is kind of a strange business. Sometimes we worry about algorithms like bisection and Newton's method, secant, false position, and so on. Other times we worry about floating point arithmetic issues, as we've done recently, but also there's mathematical theory involved. So today I want to talk about fixed points of functions and fixed point iteration. If I have a function g and x is a number that obeys g of x equal x, we say that x is a fixed point of the function g. As an example, let's look at the function g of x equals x squared plus 4 divided by 3 times x. Obviously, I need to stay away from x equals 0, but assuming I am not there, what kind of fixed points does this function have? What does it mean for g of x to equal x? Presuming that x isn't 0, we can get rid of the bottom of the fraction by multiplying by 3x. Then you can divide both sides by 2, and you find out that x squared and 2 have to be the same number. There are two things that would make that work. One of them is negative of principal square root of 2, and the other one is the positive square root of 2. This function, g, has two fixed points. Another example would be g of x equals x squared plus x minus 2. Let's look for any fixed points that that function may have. If you write down what it means for x to be g of x, and then simplify and solve that equation, you'll find out that this g function also has two fixed points, and they are the same points that the other function had, even though this is a different function. Back when calculators first came out, there was something that we nerdy people liked to do. It's not quite as nice to do these days because I have to type more, but on the old calculator, you would type some number in and then start repeatedly hitting the square root button. Let me show you what I mean. I'm just going to pick some number, take the square root of it, then take the square root of that, then take the square root of that, and so on and so forth. On the old calculators, you could just do this by pressing a single button. Here, I'll raise my numbers to the 0.5 power. So I'm going to take 6 and raise it to the 0.5 power. Then I'll take that and raise that to the 0.5 power. Then I'll take that and raise it to the 0.5 power. I'll do a few more of these without vocalizing it. If you look at these numbers, a suspicion begins to form in your mind. If you kept doing this a long time, I bet the numbers would get really close to 1. So I'm taking a number and I'm doing something to it. whatever I get for the result, I do the same process to that result, and I just keep on repeating. One thing a person might ask themselves is, does this behavior depend particularly much on what that first number you put in was? So let me repeat myself. It sure doesn't look like it. Based on this extensive research, that is 2 tries, it looks like if I pick a positive number and start feeding it into the square root function over and over and over again, it looks like I might settle down to 1 after a while. Given some initial number x1, I'm going to let x2 be g evaluated at x1, x3 will be g evaluated at x2, x4 will be g evaluated at x3, and so on and so forth. Or more compactly, x number k plus 1 equals g of x number k. This is called fixed point iteration. We've got a very useful fact that we'll actually demonstrate here in a second. It's this. Presuming that our g function is reasonably nice, it's continuous, doesn't have any breaks in the graph or asymptotes or anything like that, the following statement is true. If the fixed point iteration, this iteration, converges, then the thing that it converges to is a fixed point of this g function. Let's suppose that the fixed point iteration converges to some particular number that I'll just call x. So that I don't bias myself, I'll represent that as x equals the limit as some letter tends to infinity of x with that index from the fixed point iteration. The limit as the index becomes indefinitely large of x with that index converges to x. So I don't mind writing this equals that because I know that this limit converges, and these numbers equaling these numbers means this limit converges too. For a continuous function, the limit as k tends to infinity of a function value evaluated at x number k is the same as the g function evaluated at the limit of the xk's, but the limit of the x indexed numbers is this number x. So this tells me if g is continuous and the fixed point iteration based on g converges to something, then that something, the x, must obey the equation x equal g of x. This means that this x is a fixed point of the g function. I'd like to go back and think about my g of x equals x squared plus 4 over 3x function. I'm going to try to find a fixed point of it using this fixed point iteration. Now, of course, we already know what the answer is, but I'm pretending that I don't here. I'm going to use my calculator tricks to make this less painful than it would otherwise be. I'm going to start at x1 equal to 3. I store 3 into my x variable, and I calculate the value of g at that x. I get 1.4 repeating. Then I'm going to store that into the x variable. Second enter, brings my compute line back up, and I'll press enter on that and get 1.404 some odd. If I were doing this in a problem, I would want all of those digits. Store into x, second enter, second enter, recalculate, 1.41 some odd, store into the x variable, and these numbers are approaching some number that's in the neighborhood of 1.4, which is the neighborhood of square root of 2. If I were to continue doing this for a while, then this fixed point iteration would converge to square root of 2. Now, I don't want you to get the wrong idea. Just because a function has a fixed point doesn't necessarily mean that the fixed point iteration is going to converge. It looks like it worked very nice on that problem, but x squared plus x minus 2 has the same fixed points as this one, but it's going to act differently. Like before, I'm going to start at x equal 3, and now my g function will be this quantity. That's not good. I'll store that into x and then do my double second enter trick and press enter again. That's even less good. That's even more so in the not good sense. This doesn't seem to be working. Now, an optimist would say, well, no approximation method is perfect. Maybe we just didn't start close enough to the solution. We know we have fixed points at plus or minus radical 2, so how about we start pretty close to one of those numbers? So I'll reset the value of x to be 1.5. The actual principal square root of 2 is 1.41 some odd, so this is pretty close. Morning, Roman. So let's calculate. This is further away from the square root of 2 than the 1.5 that we started with. Nope, it's not going to work. It's being pushed away from the solution instead of being right at it. How about if I start really close to the square root of 2? I looked at it previously. The square root of 2 is about 1.4142135. So this is really close to square root of 2. That's actually a little bit worse. I'm now at 1.4113. I'm losing accuracy instead of gaining it. If we were to do this some more, it would continue to get worse. Being mathematical types, The obvious question is there some reasonably simple condition or criterion that will tell me whether I'm going to have convergence or divergence? If the answer to this question were no, I would just be playing a practical joke on you. So obviously the answer is yes. To look into this, we need to know something called the mean value theorem, which you learned back in the first semester of calculus and probably seemed so pointless and useless that you've forgotten it by now. It's going to be very important to us, so let me remind you. If you want to be sort of overly official about this sort of thing, we would say, given a function g that is differentiable on some interval of numbers from a to b, there is, backward z, there is a number c in that interval so that g prime at c is g of b minus g of a over b minus a. When you put it like that, it seems to be complete gibberish. Let me draw you a picture. Since g is differentiable, g is continuous, meaning not only are there no breaks in the graph, there's no sharp corners either because the derivative is the slope of the tangent line. I don't know what exactly the graph of g looks like. It could, for instance, be a straight line or a parabola. It could oscillate. It could do lots of things. It might do that, for instance. What the mean value theorem says is someplace between A and B, there is at least one place where g prime at c, which is the slope of the tangent line on the graph, is the same as the slope of that straight line. Let me take some of the fancier language away still. Somewhere between A and B, there is a tangent line that's parallel to this line. So, for example, roughly speaking, there might be such a place. There's probably more than one on a general graph, but the mean value theorem says there's at least one. So let me take even more language away. What does the mean value theorem say? Somewhere on this curve, there's a tangent line that's parallel to that line. That's all. So this is what we mean by the mean value theorem. What this has to do with anything is not clear at all, but it will be shortly. So I want to think about this fixed point iteration business. The letter x by itself is the value of the fixed point. It's the x value where x and g of x are the same number. Even though I don't know what x is exactly, I can subtract it from both sides of that equation. On the left, I already get something of interest. This number is how different estimate number k plus 1 from the fixed point method is from what it is that I'm trying to figure out. This side is less transparent until I remember that x is a fixed point of g. X, that x, is the same thing as g of x. At first glance, this seems to make things more complicated instead of less, but we're going to do a bit of trickery here. I'm going to divide this side by xk minus x, and then multiply by xk minus x so that I haven't done anything. Again, this looks like I'm making life harder on myself instead of easier, but we'll see in a second. This number measures how different x number k plus 1 is from the answer that I'm trying to get. That number multiplies by some constant here, but by itself, xk minus x is how different estimate number k is from what it is I'm trying to figure out. But the mean value theorem says the difference of the two g values divided by the difference of the two x values is exactly equal to g prime evaluated at some number ck, which is located between x and x number k. I don't know if some of these estimates are bigger than x or smaller than x, so to remove all plus or minus sign confusion, I'm just going to take the absolute value of both sides. Suppose that the derivative of the g function never got very big in absolute value. Maybe it's always smaller than 1/2. Then that's going to tell me that the new distance on the number line between xk plus 1 and x can't be bigger than half of the previous difference. That tells me every time I do a step of this fixed point method, I'm going to get moved closer to the solution than I was previously by reducing the distance by at least a factor of 1/2. On the other hand, suppose I knew that the g prime was always bigger than, say, 2 in absolute value, then the new error would be at least 2 times the previous error, and things would get worse as I went along. So what's going to control convergence or divergence of this fixed point method? It's how big g prime can get. Imagine looking at the fixed point. Look at the value of the derivative of g there, and you find out that it's less than, say, 1/2 in absolute value. If I assume that g prime itself is continuous, which isn't a very big assumption, then close to this particular x, g prime will have to be less than 1 in absolute value. What that means to me is that if I pick my x1 within this interval and do a step of the fixed point method, I'll get x2, which will be closer to x than x1 was. Then I repeat this process, and it's like reeling a fish in. If the absolute value of the derivative never gets bigger than 1, it's going to be like the iterates are magnetically attracted to the fixed point, and things will go our way. On the other hand, the case we don't want to see, in this interval, say, suppose that you knew the absolute value of g prime was at least 3. When I do a step of the fixed point iteration, I'm going to be pushed away from the solution by a factor of 3, not pulled into it. So let me use very abstract and scholarly looking language here. If this happens, I'm happy because my fixed point iteration is going to work as long as I start in the nice interval. If this happens, I'm not happy because I guarantee you that it's not going to settle down to that. I suppose a miracle could happen, and if you accidentally started right at the answer, then you could sort of say you get convergence, but that's not very likely, and we can't count on that So let's return to our two examples. The one that worked out nicely for us was g of x equals x squared plus 4 divided by 3 times x. I need to know the derivative of that function. I'll use the quotient rule from Calculus 1. Firstly, I want to look at the value of this derivative at the positive fixed point at x equals radical 2. At such a place, x squared will just be 2. Right at the fixed point that we're trying to find, the value of g prime is negative 1/3. The absolute value of that is 1/3. 1/3 is less than 1. As long as I don't get too far away, the derivative will be smaller than 1 in absolute value, and I'm in the good situation. There's going to be an interval in which, if I take my starting point within that interval, the fixed point method will work. What about the other one? This is a much simpler looking function, so an optimist would think things will be even better. In this case, the digits in the value of g prime radical 2 are absolutely not important to me, because any way you slice it, it's a positive number plus 1, which is bigger than 1. This means even though this function is simpler, its fixed point properties are not so good at all. This says even if I start near but not right at radical 2, if I do a step of this fixed point method based on this function, the error is going to get worse by almost a factor of 4. This tells me that that fixed point method will not work. This is the main point of what I was wanting to talk about today. During our next meeting, we'll talk about Newton's method as a fixed point method, for which we'll have to recall Taylor's theorem with remainder. We'll talk about what we mean by a simple root and a root of multiplicity, and also we'll talk about something called modified Newton's method. Until then, I hope you all have a good day, and I'll talk to you again soon.